All right, let's pick up where we left off. Let me move that a little bit. There, come down. So we're on part B. Part B says pre-reaction complexes. Aryl halides, which can act as electron-accepting ligands, could form stable complexes with the electron-rich unsaturated PDPP fragment and were thus investigated as potential pre-reaction complexes in Aryl X activation. There are, in principle, several coordination modes conceivable for an Aryl halide. In analogy with the related oxidative addition of Aryl CH bonds, where, for example, platinum 0, platinum 2, or rhodium 1, eta squared, arene complexes, I don't know if that's correct or not, were experimentally shown to be involved. We considered the coordination of the aryl halide in an eta squared fashion, both pp on one side, now to look at that, PD, 1,2 phenyl halide, so that's 3.1x, and 2,3, 3.2, so let's say x. Complexes were studied in which respectively the carbon ipso and carbon ortho, or the carbon ortho to carbon meta bond of the aryl halide coordinates to the metal center. All right, so let's go back. So that was saying, right. So this comes back to this. It says, oh, what's going on there? Can I do that? Nope. Oh, I can do this. So hopefully there won't be an echo. Oh, hopefully there's no. All right. Oh, maybe this one. Yeah, there you go. All right. So yes. So this is the carbon 3,1 that is attached to the aryl, to the halogen. And that is going to be, all right, respectively, ipso-ortho and ortho-meta bond of the aryl halide coordinates to the metal center. So both 3.1 and 3.2 complexes were studied in which respectively, so ipso-ortho has got to be 3.1x, ortho-meta. The 3.1 is ipso-meta, ipso-ortho, ortho-meta, ipso-ortho, and this one is going to be ortho-meta. Oh, got it. So the ipso carbon, there we go. The ipso carbon is that one, I think, and the ortho is going to be that one. Carbon ortho, and this one's going to be or wait a minute, 3,2. All right. So the complexes we're talking about, where'd my piece of paper go? So we're talking about 3.1 and 3.2. And we've got PD, and we've got 4 spots. And let's just draw them like this. And here we've got a PP, so let's just be TMPE, which is going to be phosphorus, phosphorus. Put my methyl groups out to the side. And then I'm forming a complex between, this might be the world's biggest. This is, so there's going to be this to the carbon there, and then there's the complex to this carbon, and then well, I think I did that wrong. Oh, right. I spaced them out. So that's the right idea. And then how is this different? All right, sorry, let's get it on screen here. So we've got this carbon and this carbon, so and 3.1, and then 3.2, we've got PD, we've got at least for the DMPE. And now let's see if I can draw this a little better. So the X is higher. So the X is up here. X comes there. Oh, I see. All right, I have drawn it wrong. I apologize. Let's try again. So the two bonds, or these two down here at the bottom, I think. Yeah. So let's try drawing that again. So 3.1 is going to be, right? So, because let's zoom in here, stream close up. All right. Hold the focus right there. I think it's too close. There we go. So there's two bonds going down to the two carbons at the bottom. And the one's a dash line because it's behind, and one's there. So the two bonds are going to be the bond ipso is the one associated with the halogen, and it's going to be the one next to that. And then ortho and meta is going to be, right, the ortho and meta, and then the para is not attached. And the X is just up here. Okay. Maybe we don't have to draw it then. That was the problem. So this is, so, all right, extreme zoom out. Carbon ipso is attached to Aryl, and ortho is next to X. So C next to CX. And this is C next to CX and the one after that. So the new term is ipso. Ipso is the carbon attached to the aryl group, or attached to the halogen group. Sorry that took so long, but all right. Respectively, the carbon attached to the halogen and the one next to it, or the one next to it and the one farther away. Bond of the aryl halide coordinates to the metal center. Both were studied. Another possibility is the monodentate coordination through the halogen atom, as demonstrated for a group 10 metal in where, so this is a reference, and it says the halogen itself coordinates in a monodentate way. So this refers to the X coordinating with the palladium in a monodentate way. 1 bite. The other one with 2 bites off of the palladium. All right, reaction energies for the coordination of benzene or phenyl X equals these halogens to 2, yielding 3,1 to 3,3 are collected in table 1, and optimized structures are shown in figure 3. The reaction is exothermic in all cases. Good. Irrespective of the combination of ligand, phenyl halide, and solvation state. Well, I think this sort of makes sense because we've created a very high energy complex when we take away one of those PPs. And that was seen in these very positive numbers up at the top here of table 1. So the eta squared arene complex is 3,1 and 3,2. All right, I have to admit, I'm going to look up eta symbol. It does sort of look like that. Greek alphabet. There's no other one that looks like that. I guessed correctly, although I may have guessed incorrectly at other ones. Yes, that's eta, which the lowercase looks like an N with a long line, and the uppercase looks like an H, it turns out. All right. The eta squared arene complexes 3.1 and 3.2 are generally favored over 3.3. So the halogen doesn't monodentate coordinate, is what they're saying. Let me make sure I'm on page here. Yep. The electron accepting arene being a better suited ligand for the electron-rich D10 metal center. The DMPE complexes 3,1A and 3,2A are more stable than their BMAP analogs by 20 kilojoules per mole. So if we come over to this table, then at 1 to 2, the BMAP ones, we said were about 25 kilojoules. Are we in kilojoules? Yes, kilojoules per mole, more stable than the DMPE ones. And then as we go here, right, these numbers are 20 kilojoules higher than these numbers. Right. And then the 3,1x and the 3,2x's appear pretty similar in my reading of this. Let's see. This preference for DMPE in the formation of the pre-reaction complexes almost fully compensates the advantage of BMAP in the preceding dissociation step, making the DMPE and BMAP arene complexes equally stable relative to 1. Okay. And the arene complexes, so arene, it would be ene has a double bond, and air means aromatic. So the aromatic double bonded things are what is going on for an arene. The influence of solvation on the energetics of the formation of the pre-reaction complexes is 3,1 to 3,3 is generally small. So right, so that's the 2 columns, gas versus THF. We see small decreases. Okay. Varying between -6 and +9 kilojoules per mole. A notable difference between the 1,2 eta arene complexes, 3,1, and the 2,3 eta complexes, 3,2.2, is the influence of the halide. Whereas the formation of 3.1, where the aryl halide C ipso atom is directly attached to palladium, becomes more favorable along the series. So more favorable along the series chlorine to bromine to iodine. So this is going to be 3,1. Chlorine to bromine to iodine becomes more favorable as you go down, more favorable, more favorable, more favorable. The stability of 3,2, where C ipso is one position away from the ring atoms interacting with the metal, remains unaffected by the halide. So you're not dealing with the carbon attached to the halide. The one result of this is the halide, whatever the halide is, doesn't matter. And so that means as we go to 3,2, 87, 88, 89, negative, right here. 85, 85, 85, 70, 71, 71. Yes. So, oop, halide. Oh, halide. No effect. And up here, iodide, more stable. Iodide, more stable. All right. The structures of the PDPP, moiety in 3,1 to 3,3, figure 3, reflect the strength of the interaction with the aryl halide ligand. In the arene complexes 3,1 and 3,2, the PDP bond lengths and the PDP angle take values similar to those in the coordinatively saturated one. In 3,3, on the other hand, where the aryl halide is relatively weakly coordinated, the PDPP fragment is structurally closer to the unsaturated 2 with shorter, all right, but we don't really care about the 3.3. So, but yeah, that's okay, interesting enough. These differences are only weakly affected by the type of diphosphane ligand or halide. Solvation slightly elongates the PDP bonds. The eta squared coordination of the arene ring to the metal in 3,1 and 3,2 is unsymmetric. The carbon atom closer to the halide, that is C ipso in 3,1 and C ortho in 3,2, going up, is always more strongly coordinated than the other carbon. And how do we know that? Because the bond length is shorter? Yeah, that's funny. So if we come over here, we have, now we're at 3,1, PDC1, right? And we've got optimized structures of the pre-reaction complexes 3.1 to 3.3, where structural data are arranged in 3 columns. They refer to the chloro, bromo, and iodo compounds, respectively. See caption to figure 2 for further explanations. So, okay, right. So here we have, remember, so square brackets mean THF. No brackets mean gas. Oh, yeah. And then, so this is going to be chloro, bromo, iodo, always. And then we have, okay. So then this is going to be gas. This is going to be TH, no. 2 columns, italics. So, gas, italics, THF. So this is gas, this is THF. This is Oh, BMAP. So these are, so this is gas THF BMAP. Yeah, it's tiny, but it says BMAP. This is THF and gas, and this is DPME. Hope that's the right one. All right. So things are very much the same here for the palladium carbon 2. For the ipso, this is, so ipso C ortho. This is C ortho, C meta, because, right, there's the halogen, C1, C2, and C3. They're forming complexes. All right. I wonder if this would be easier to do if it was not in black and white. But yeah, so this is the type of data we want to put out, and these are the kinds of pictures we want to do. These are ball and stick. These are probably ChemDraw. Excuse me. But I think one thing I'm going to do is I'm going to turn the background of my Gauss view from purple to white. Although then I won't be able to see, well, you can still see the hydrogens. Anyway, we have to figure out how to make these beautiful drawings, I think. All right, so yes, we know how to interpret these drawings now. And now we come back to here. Oh, yes, so the ipso and ortho, the closer one, are always more strongly coordinated. We're going to look at the bonds lengths. So C1, 1.8 to 2.3. And here, 2.2, 2. Oh, this is 2. Never mind. This is to the halogen. So yes, that's going to get bigger as you go from chlorine to bromine to iodine. Here, palladium to C1. These are always lower than these. So the palladium to carbon 1 is always lower. And in fact, it gets smaller as you go this way. So as you go from chlorine to bromine to iodine, the C1 bond gets shorter and stronger. And here, I would say the C2 stays basically the same. And here, that literally stays the same for C3. C1 with the halogen changes, palladium, no change. So, no change in the bond length between the palladium and either a carbon in 3.2, which is the ortho and metacarbons of the benzene ring. I think we're figuring out how to read these pictures. And I think we just showed that it's more strongly coordinated than the other carbons. So equals, come on up there, shorter bond. All right, stronger bonds are have more energy stored in them, and they're shorter. This difference, delta, between the two PD carbon bond lengths varies significantly for the different arene complexes. And 3.1a in the gas phase, it increases along the series ClBrI. Nope, it doesn't go that way. And THF, it is another 0.03 angstroms larger. And 3.2, however, it is 0.02 irrespective of the halide or the solvation state. The same pattern is observed for the corresponding BMAP complexes 3.1b and 3.2b, although slightly less pronounced. The strength of the PDC interaction is mirrored in the CX bond. The shorter, stronger is PDC. The longer, weaker is CX. Hence, in 3.1a in the gas phase, Cx is elongated relative to the free aryl halide. So this bond is getting longer as this bond is getting shorter. An additional elongation of 0.03 angstroms, going to 0.08 angstroms, is found in solution. For 3.2a, the lengthening is small and independent of the halide and solvation state. Again, the structural effects are analogous, but smaller in 3.1b and 3.2b. The length of the CX bond, blah, 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 blah. Okay, so there are some trends. And we have another half page to go. The trend of, but we're seeing a lot of trends, and we're going to want to interpret the trends that we see from ours in very similar ways, because we're forming, Will was talking to me about the complex and how to tell where it was, and I'm still unclear as to why it is, but I mean, I guess I'm starting to understand that if you have a palladium with two trimethylphosphines and you have a aryl or benzene chloride or bromide or fluoride, that they have to come together in some way. So, and I think what we're doing is we're putting the carbon and something else, and the chlorine, right, the carbon and the chlorine closest to the palladium and trying to form some sort of pre-transition state complex that then breaks this bond and forms the two bonds between the halogen and the carbon. Okay, that makes sense. So if you're going to break bonds and make bonds, you're going to have to get those bonds pre-formatted. But then the transition state complex, right? Yeah. So the transition state complex is going to be the maximum energy state between the complex, well, between the reactants, but then in addition, between the complex and the products. So somewhere on, all right. So let's see. So this is a reaction energy diagram. Typically looks like this. If it's exothermic, we've got reactants, we've got products, we've got transition states. And then we're trying to find, in addition, some free transition state complex. And it must be between the reactants and the transition states in position and energy. And so I guess we should be able to, not that we necessarily care, but maybe we do, is at least we know the reactant, we know what the transition state is, we know what the products are. So we should be able to pick out that spot in energy, that spot in energy. And I'm not sure why, probably because it helps us to elucidate or determine the mechanism. We're going to be interested in this spot, reactants to transition state, see if it makes sense, right? So all this is computational modeling. So we're going to see if it makes sense physically, because we can calculate lots of things. Okay, I think, well, anyway, maybe that makes sense. We're getting there. All right, we made it all the way down here. Trends observed in 3.1 of increasing phenyl halogen bond activation and better stabilization along the series Cl to Br to I can be rationalized. Yes, we're going to be rationalizing by inspection of the pertinent orbitals involved in the interaction between the phenyl halide and the metal complex? Figure 4. All right. Figure 4. All right. So now it is a sketch of the orbitals involved in the interaction between the PDPP complex 2 and the phenyl halide. Depicted are the HOMO of 2 and the 3 lowest unoccupied levels of phenyl halide. The orbital C is significantly stabilized along the series CLBRI. Okay, so this seems to be saying that A and B stay the same, but C changes from higher energy for chlorine to lower energy for iodine. Huh. So, all right. I wonder if it's going to tell us how they know this. The interaction is dominated, come on, by back bonding from the electron-rich palladium. Oh, did we skip this somehow? Oh well, looks pretty interesting. All right. The interaction is dominated by back bonding from the electron-rich palladium, D10 center of 2, where 2 has its very high energy because 2 has one of the PPs missing. 2, 4, 5. All right. To the phenyl halide acting as the acceptor. Back bonding. That's a term I probably want to look up. Back bonding. All 3 phenyl halides have 2 low-lying empty orbitals of C ipso ortho and C ortho meta pi antibonding character, respectively, suitable to interact with a filled d orbital of palladium. Wow. Which accounts for the eta squared coordination mode in both 3.1 and 3.2. So wait a minute. So we're forming an anti-bonding orbital here. All right. Pi anti-bonding character. Because anti-bonding orbitals are higher in energy. Let's see. So C is anti-bonding because it's bringing together 2 different, right? It's got this thing in the middle, the space. Huh. Oh, let's see. But I guess they are the, let's see. Come on, let's move that up. Better. All right. All right. Permanent orbitals and all 3 phenyl halides have 2 low-lying empty orbitals. So of C ipso and ortho and C ortho and meta pi bonding character, pi anti-bonding character. So we've got lowest unoccupied molecular orbitals and with pi antibonding character, and highest occupied molecular orbitals is a D of the palladium. So suitable to interact with a filled D orbital of palladium. Oh, I haven't used any other colors yet. The energies of these orbitals are essentially unaffected by the halide. However, there is a low-lying sigma star, so sigma antibonding CX, right, antibonding orbital that is the more strongly stabilized, the less negative X, electronegative X is. Its energy decreases from minus 0.76 electron volts in phenyl chloride to minus 2.25 electron volts in phenyl iodide. So there are no numbers, but they're saying, so this is a sigma star pi. So it's a sigma orbital, it's antibonding, that's made from pi orbitals. It's antibonding because you have areas of different phase. Sorry, I had to pull that word out. Next to each other. And destructive interference. And then these are, let's see, B and A. A is lower in energy than B. Oh, hold on. So, slowly but surely figuring this out. So here is the palladium D orbital, and it's filled. It's the HOMO. Oh, HOMO, highest occupied molecular orbital. And here are the three LUMOs for the benzyl halide. All right, we're slowly but surely. So this is the halide. The halide is not involved in A. It's a antibonding molecular orbital associated with these carbons of the benzene ring. And here we have B, which is 1, 2, 3, 4, 5, 6, 7 different orbitals and antibonding as well. It's probably A is probably these are all probably antibonding because the bonding ones are full. All right, and so since this one for here is right, so it changes a ton in order to be, that's why it changes from minus 0.76 to minus 2.25 electron volts. All right. And so on. To minus 2.25 electron volts in phenyl iodide, where it even becomes the lowest lying molecular orbital, LUMO, while it is LUMO plus 2 in phenyl chloride and phenyl bromide. This orbital can participate in metal phenyl chloride, phenyl halide bonding only in 3,1, but not in 3,2. And hence this explains the halide dependence of stability and CX bond activation in 3,1. Right, because the carbon halogen bond in 3,2 is one carbon away from all the action. It also accounts for the trends observed in 3.3, where the halogen actually bonds monodentate with the phosphorus. Not that we care. We don't anyway, they did. All right, so summarizing the results for the pre-reaction complexes 3.1 to 3.3, we note that all three types are stable relative to the unsaturated complex 2, yes, much lower in energy, for all combinations of diphosphane, halide, and solvation state considered. The carbon halogen bond is in all cases activated to some extent. The phenyl halide kappa X complexes 3.3 are the least favored, why we don't care. Moreover, in the context of aryl halide oxidative addition, they appear to be of potential interest only as intermediates in an inner shell single electron transfer mechanism, blah, blah, blah. Such a mechanism is, however, experimentally not supported, and we will thus not consider complexes 3.3 further. The eta squared arene complexes 3.1 and 3.2 are of comparable stability. However, the CX bond is more strongly activated in 3.1 due to the more favorable interaction of the metal complex with the phenyl halide. Furthermore, in 3.1, the phenyl halide bond is suitably oriented relative to the metal center for a concerted oxidative addition process. Therefore, we focus on the following on the 3.1 as pre-reaction complexes. All right. Phew. I feel like we're getting somewhere. So I still haven't figured out how we just totally missed this figure. Oh, we didn't need this figure because we were looking at all these numbers. And I think we'll stop there.